Welcome to Session 7. In this session, we'll discuss two very important techniques, input scaling and dimensional reduction. The problem we have with our neural networks is that unimportant input can slow learning, or worse, is noise that is learned by the network. What we need is a quick way for our learning algorithm to detect and remove these unimportant inputs early on. We can't rely on our fully connected networks to remove these inputs because each input is connected to n different neurons, which means that n different numbers need to be adjusted. This takes too many iterations and is not guaranteed to succeed. The other problem we have is that outliers can dominate batch learning. We also want a way to automatically reduce the effects of these outliers without making too many assumptions on their distribution function, etc. This is where input scaling comes in. We have our input, and what we do is we take them and multiply them by these lambdas, which are factors. This solves problem number one because we can very quickly reduce or change each lambda individually, and this is just one number that we need to change. This vector is taken and clamped using a 10 hitch, and this solves our second problem, which is outliers. Input elements with outliers will be clamped because of the hyperbolic tangent function, and the clamped values become the new input into the main network. To summarize, input scaling allows us to remove or reduce the effects of unwanted inputs quickly because we just use one lambda per input. We use also a symmetric squashing function like the hyperbolic tangent because we can use it to reduce the effects of outliers. One other thing is that we need to constrain the values of the lambdas so that they are always positive. This is to prevent lambdas with large negative and positive values from cancelling out each other. Our next strategy to help neural networks learn is called dimensional reduction. It starts with the observation that neural networks don't really work well with large dimensional inputs. In fact, the smaller the dimension of the inputs, the better. We can reduce the dimensions of the input vector using something called an autoencoder. We start with an input vector x and we pass this through a 3-layer network called an autoencoder. What we do is we constrain the output to be the same as the input. In other words, we want x reconstructed to be the same as the input vector x. We discard the reconstructed vector and instead tap the center portion or the bottleneck as the reduced input. When using an autoencoder, 3 layers is more than enough, and you want to use a tangent hitch again because it saturates evenly at both ends. You also want to use a compression factor of half or even more. This means that there are half as many neurons or less in the middle bottleneck layer. Always check for good reconstruction. We train this subnetwork simultaneously with the rest of the network, but with a separate loss function. Here is a typical graph of the separate loss function that we track, and the goal is to get as small as possible a reconstruction error. I'd like you now to start on labs 3 and 4 of NN102. Good luck.